All right, so now we want to look at skeletal structures. Skeletal structures are an incredibly useful tool for drawing organic structures. And when we're drawing the skeletal structures, there's a couple of things we can do. Well, first of all, it's a shortcut for drawing Lewis structures. We can represent all the same information that a Lewis structure has, but with a lot less effort. And if there's one thing that you find about chemists, scientists in general, is that we're a little bit lazy. We like to have shortcuts. And so that is what we do. So the way that we do it is that we assume there is a carbon at the junction of any two lines or at the end of a line. And we also assume that there are enough hydrogens. The hydrogens are implied when we're doing skeletal structures. So there are enough hydrogens to make it so each carbon has 4 bonds. In other words, tetravalent. And then we draw any heteroatoms in expressly. Carbons aren't labeled. They're just implied by the connection of 2 points. Hydrogens aren't drawn unless they're on heteroatoms. And then here are a couple of examples of some Lewis structures and their corresponding skeletal structures, just to show you how much easier it is to draw these skeletal structures. So the end of a line is just going to be a carbon. Since there's only one line going away from that point, that means that there are 3 hydrogens on that carbon. All of these carbons where there are 2 lines that come together to form a point, there are 2 implied hydrogens on those. And so you can see, instead of having to draw out 6 carbons and 14 hydrogens and all the lines that are in between, you just draw these 5 lines and you've got hexane. It's just so much easier to draw these skeletal structures. Once you get used to drawing skeletal structures and interpreting skeletal structures, you're going to prefer using them. At least, I hope you do. All right. So here we've got the Lewis structure for cyclohexane. Cyclohexane, C6H12, and you'll notice that each carbon has 2 hydrogens on it, and that they are all in a ring. All 6 of those carbons are in a ring, and so we simply draw a hexagon, and draw a regular hexagon, and the 2 hydrogens on each carbon are implied. All right. So when it comes to interpreting them, very similar, and we're going to practice both interpreting and drawing skeletal structures here in just a moment. But when it comes to interpreting the skeletal structures, each point that isn't labeled must be a carbon. So if it's not labeled as a heteroatom, it must be a carbon. So for example, here we've got this hexagon with a line on it, and then we've got this line and then NH2. Well, all of those points at the end of the lines and at the intersection of any 2 lines must be a carbon. And then if there's less than 4 bonds going to any of those, then any remaining up to 4 is going to be hydrogens. So this particular carbon here is going to have 3 hydrogens on it. This one already has 3 lines going to it, so there's only 1 left, so it's going to have 1 hydrogen on it. All of these over here that are the intersection of 2 lines are going to have 2 hydrogens on them. The only hydrogens that we have to draw that we can't leave off are ones that are on heteroatoms. So you just count the number of lines going to each carbon. If it's less than 4, then add enough hydrogens to give each carbon 4 bonds. And then we add lone pair electrons to any heteroatoms as needed if we're going to draw the Lewis structure. Here we've got acetylene, so we've got a line, a triple line, and then a line. Well, that's 4 points, and each of those 4 points is a carbon. And then here we'll put in the correct number of hydrogens. So this one has 3 hydrogens. These don't have any hydrogens because they already have 4 bonds. And of course, this one also has 3 hydrogens. Now, One thing that I want to mention, when you're doing this, you do not want to leave it in sort of this middling state. You can either have your Lewis structure, you can either have your skeletal structure or your Lewis structure, but you can't put a carbon and then not put the hydrogens. If you're going to label the carbon there, then you need to label what else is attached to it. If you're going to do skeletal, that's fine, but don't like stop here. That's a common thing that I see, particularly on the short answer section test. When I give them, I will see students forget to put hydrogens on there, and I want you guys to be able to do this properly. All right, if we have charged carbons, and we're going to see this here with other things in just a moment, but if you have charged carbons, then the charged carbon takes the place of one hydrogen atom. So here, on these carbons that are on these particular points, they are assumed to have two hydrogens on them, but this one, that positive charge, takes the place, so it only has one hydrogen on it. That means that this particular carbon does not have a full octet. This takes a little bit of getting used to, so you're going to have to practice this to get good at it. Here we've got, again, we've got the hexagon, again, all of these carbons are going to assume that we have two hydrogens on them. But here we've got a negative charge. That negative charge, the only way that happens with carbon is if there is a lone pair of electrons on the carbon. I'm going to go over to the commonly used charges that we had talked about previously. And so when there's a negative charge on carbon, there's a lone pair of electrons and 3 bonds. All right. And so that means that there are the 3 bonds and a lone pair of electrons on there. So you can either draw it just with the negative, or you can expressly draw the lone pair of electrons if needed. So negatively charged carbons will have a lone pair as well. All right. When it comes to heteroatoms, the lone pairs of electrons on heteroatoms, well, you don't have to put lone pairs on heteroatoms. You don't have to expressly put the lone pairs, but sometimes it's useful to put them, particularly if we're doing mechanisms. And when we get to mechanisms at a later point, I will explain why that is true. But it is important that you not forget that they are there. So you use the formal charge to determine the number of lone pairs that are on a particular atom. So for example, here when oxygen is neutral, as on this alcohol here, that means that there are 2 lone pairs. Again, if you go back over and look at this, well, when oxygen is neutral, it has 2 lone pairs on it. Okay. When oxygen has a positive charge, that usually is accompanied by 3 bonds and 1 lone pair. Well, we go back over here and we'll see when it's positive, it has 3 bonds and 1 lone pair. If we had the negative charge for oxygen, it would have 1 bond and 3 lone pairs. And that would give us a negative charge. So again, I want you to memorize this table. So I want you to memorize this table, and that way you will become quite familiar with it. All right, we want to go to number 62 and 64 on the in-class assignment. These are relatively straightforward. I'll make sure my camera is all lined up here. All right, so this one, it says, how many hydrogens are present around each carbon in the following molecules? So we have capsaicin. This is the hot stuff when you have a hot pepper. That is capsaicin. And you'll see that we'll just go to each carbon and we'll put the correct number. This carbon is at the end of a line. That means there's 3 implied hydrogens. So I'm going to put a 3 next to that carbon. All right, so there are 3 next to that one. This carbon, as you can see, has 4 bonds already drawn. So 1, 2, 3, 4. So it has 0. Hydrogens on it. This one is the same with 0, as is this one right there. That one has 0 as well. If we look at this particular carbon, it's got 1, 2, 3 that are expressly drawn. And with 3, that means there is 1 hydrogen that is on there. Same thing with this one and this one. If we look at this carbon, there are 2 bonds that are expressly drawn. That means there are 2 implied hydrogens that are there. On this one is similar. So 2, 2, 2, and 2. Those all have 2 bonds going to them that are expressly drawn. That means they each have 2 implied hydrogens. Oh, this carbon has 4 bonds going to it. It has 0 implied hydrogens. That one is an amide. Here we've got 3 bonds going to it, so there's 1 implied hydrogen there and there. This carbon has 1, 2, 3 bonds going to it, so it has 1, and then each of these has 3 implied hydrogens. All right, so now let's come over to this molecule. This one's fexafenidine. I looked this one up. It is an antihistamine. I didn't recognize the brands for it. Looks like it is a pretty decent one. It's supposed to be non-sedating, but can cause some drowsiness. So be careful when you're taking it. All right, so on this, we've got these benzene rings. Eventually, you're going to become almost automatic when you're doing this. You'll say, okay, at that attachment point, there are no hydrogens on those carbons because there's 4 bonds going to it. So 1, 2, 3, 4. So that's 0 and 0. And then for all of these, there are 3 bonds going to all of those. So 1, 1, 1, 1, and 1. Similar here, 1, 1, 1, 1, and 1. The carbon that is here has 4 bonds, 1, 2, 3, 4. So there's 0 on that carbon. This carbon has 1, 2, 3 bonds. So there's 1 on that carbon. And then 2, 2, 2, and 2. All right, that nitrogen, there is a lone pair that is present on there. That's not a big deal here, but there are no hydrogens on it, but there is a lone pair. It's just an implied lone pair. For here, we've got 2 lines, so there'll be 2 hydrogens there, there, and there. This one, there's 3 bonds, so there's 1 implied hydrogen. There's 0 and 0 for those. 1, 1, 1, and 1. This carbon has 4 bonds, so 0, and then each of these has 1 bond going to it, so 3 implied hydrogens. This carbon is a carboxylic acid. It ends up having 0 hydrogens directly connected to it. What that looks like if you had R. R is just the big group here. COOH, that's the same as R. Like that. So there are no hydrogens on that particular carbon. We'll talk about that functional group in much more detail in later chapters. All right, for this next part, there's a couple of tricks you can do with this. I want you to be good at this. I guarantee that on your exam, there will be at least a couple of questions where you have to either match the skeletal structure to a Lewis structure or to a condensed structure like this, or if it's the short answer portion where you will actually have to draw. These. So let's go ahead and count here. So let's count the total number of carbons. There's 1, 2, 3, 4, 5, 6, 7, 8. And it's worthwhile to kind of put that number over on the side and make sure that you have 8 carbons when you are done. Now let's figure out what the attachment is, what the connectivity is. CH3,2 means that there are 2 CH3s attached to this particular carbon. And then we have, so we're going to have a CH3 that's attached to a carbon there, and one that is attached to a carbon. So CH3 and CH3, those are there, and then this is the CH that is there. So we've accounted for 3 of the carbons. We'll do the 4th, 5th, and 6th here. So, okay. And so that accounts for this one, and this one. And then for this one, we've got 2 methyls attached to it. And that is going to be our structure. All right, and I'm going to go ahead and count. So we have 1, 2, 3, 4, 5, 6 carbons in the main chain, and we've got 2 methyl groups on that carbon. So it's worthwhile to count the total number of carbons. Now, another trick you can do is to try to figure out how many carbons are in the main chain before you start sketching it out. And then once you do that, just sketch out that main chain and then start putting in the remaining atoms. So we have CH3, CH. The parentheses here mean that that Cl is attached to the carbon that is before it. So this chlorine is not in the chain, it is attached to that carbon. We have a CH, and again, parentheses, that OH is attached to this carbon. And then CH3. That means 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. All right. And then our second carbon has a chlorine on it. And our third carbon has an OH on it. All right. And then there is our CH3. So that is our final structure. All right. This one we have CH3. 3C. That means there's 3 carbons that are attached to this particular carbon. And then, so that's 4. Here, I never did put there was 4 over there. So 1, 2, 3, 4, and then there's 5 of these. So 4 plus 5 is 9, and 1 more is 10. So we have 10 total carbons there. Now let's count how many are in the main chain. Well, only one of these is in the main chain. 2 of them are going to be on the side. So we'll have 1, 2, plus 5 more is 7, 8. So I'll do 8. So 1, 2, 3, 4, 5, 6, 7, 8. And as we saw, there are 3 CH3s. Well, we've got one of the CH3s already drawn. And so now we're just going to draw those other 2 directly on that carbon. So this carbon doesn't have any hydrogens directly attached to it. So CH3, 3, carbon, CH2, 5, so 1, 2, 3, 4, 5, and then CH3. And that is our structure. All right, next we've got, let's count the carbons. So we've got 5 carbons, and we've got 1 nitrogen. And so it is in a ring, and I'm going to draw it in the same direction. I normally wouldn't draw pyridine this way. This molecule is called pyridine. So we've indicated each of those carbons, and I'm going to go ahead and put the double bonds in exactly the same place as our double bonds here. You'll notice that got a little bit ugly here. I'm going to redraw this because I want that structure to look a little bit better. So we'll draw it a little bit bigger. All right, we've got a double bond between that carbon and nitrogen, a double bond between that carbon and nitrogen, and a double bond, or that carbon and carbon, and a double bond between that carbon and carbon. There are implied hydrogens here, 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 and here, and there is no implied hydrogen on the nitrogen. Now, there is a resonance structure of this. This, by the way, is called pyridine. All right, pyridine is a commonly used organic base. And pyridine, there is a resonance structure. I'll go ahead and draw that resonance structure here. I'm still on the page. So, double bond there, there, and there. And that resonance structure just has the double bonds in the other locations. Those are equivalent. The electrons are delocalized, kind of like they are in benzene. All right, when you have a structure like this one, the limonene, which is an oil that you get from lemon, it has a nice citrusy flavor or citrusy odor to it. It is considered an essential oil if you're into that kind of thing. All right, so we've got a cyclohexene, but a 6-membered ring there. So I'm going to draw that as a hexagon. We do have a double bond there, so we'll go ahead and put that double bond in. We've got a methyl that's attached, a CH3 that's attached there. There's implied hydrogens there, 1 and 2 there, 2 there, and 2 there. And then we've got this as that particular substituent. And that is the structure. All right. So again, that's called limidine. It is a class of compounds that is called a terpenoid or a terpene. It's got terpenes have 5 carbons in them, and they're always multiples of 5. And there are all kinds of good smelling, not all good, but interesting smelling compounds that have these multiples of 5 carbons in them. Interesting stuff. All right, this one looks really complicated, and the key to doing this is, 1, not to freak out. So not to freak out. Oh, I forgot to put here, this one has 10 carbons in it. So the key to it is not to freak out. So let's go ahead and count the carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 carbons, and we want to make sure that we account for those 12 carbons. Now, which carbons are in the main chain? Well, this one is in the main chain, as is this one, the CH2, CH2. So that's CH3, CH2, CH2. We've got a carbon here that is in the main chain. And here we've got CH3 too. When you have CH3 as and there's more than one, those are going to be substituents. So CH3 has to be at either the end of a chain or it is a substituent. So these are attached to the side. So we have 1, 2, 3, 4. These are not in the main chain, but this one is, this one isn't, this one is, this one isn't, this one is, and this one is. So if we count the ones that are in the main chain, so 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7, 8. I miscounted there. So we'll have 8 that are in our main chain. So 1, 2, 3, 4, 5, 6, 7, 8. So that already takes care of all the ones that I've underlined there. So 1, 2, 3, 4 on the fourth one. So 1, 2, 3, 4 on the fourth one, we've got 2 CH3s. So we'll have 2 methyl groups that are coming off there. On the fifth one, we'll have 1 methyl group, a CH3. On the 6th one, we'll have a CH3. On the 7th one, we'll have a bromine. And on the 8th one, we'll just have CH3. It's worthwhile to go through and check, make sure that we have 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so that is that structure. I have no idea what that, I mean, we could name it and stuff, but I have no idea if that's a normal structure that you would find in anything in particular. All right, so we have done numbers 61, or 62, and 64. So now let's go back to our presentation. And we'll talk about orbital overlap and orbital overlap theory. All right, so when it comes to orbital overlap, in order to get a covalent bond, we need to have overlap of atomic orbitals. So the overlap needs to be between 2 orbitals that are singly occupied. We can get that with hydrogen. In the molecule hydrogen, so here is the molecule hydrogen. Each hydrogen atom has a 1s orbital, and each of those 1s orbitals has a singly is singly occupied, so has a single electron in those orbitals, and the single electron in this orbital will overlap, or the orbital here will overlap with the singly occupied orbital on this one. And when we have 2 singly occupied orbitals, they will overlap to give us a bond. And the type of bond that we're going to get here is a sigma bond. Sigma bonds are when we have overlap directly in between the 2 atoms. So sigma bonds occur when we have overlap directly in between the 2 atoms. And so the overlap is here. We will find that that overlap is cylindrical. It has cylindrical symmetry, and so it is uniform around that internuclear axis. All right. Now, sometimes things get a little bit more complicated when we go to bigger molecules. So let's look at methane. In methane, methane is CH4, just to remind everyone what that is. You maybe haven't learned those names just yet. But methane is CH4. There are 4 hydrogens that are covalently bonded to the carbon. We'll find that all 4 of those carbon-hydrogen bonds are identical. If we look at the ground state energy of elemental carbon, we will find that that ground state only has 2 singly occupied orbitals. That would imply that we're only going to have 2 bonds going to carbon. Well, that's not what the case is. We find that most of the time carbon ends up with 4 bonds. So the way that we can get around that is that we can take one of these electrons. All right, so we know carbon is tetravalent, makes 4 bonds. We can take one of these electrons from the 2s orbital and promote it up to the 2p orbital. And when we do, we now have 4 singly occupied orbitals, 4 unpaired electrons, which means that we can make 4 bonds. However, if we look at these orbitals are not equivalent in energy. And if we were to make a molecule using these orbitals, we would find that we would have one bond that is significantly different than the other 3 bonds. Well, that is not the case with methane. And with methane, all 4 of the bonds are identical. So that's just talking about the promoting up. So we'll find that in methane, we've got 4 identical bonds. And just very briefly here, I'm going to go back over to my picture. All right, and here I've got the molecular model of methane. I showed this to you guys earlier. There are 4 identical bonds, and it's in this tetrahedral shape. And so we have to figure out how it is that we can get from these orbitals to this tetrahedral shape. Well, the way that we do that is something that we call hybrid orbitals. So we're going to have hybridized orbitals of the s and the p. So carbon's orbitals can be thought of as a mixture of the s and p. So when we get that carbon that's in methane, it's a mixture of the s and the p orbitals. All right, so when we're going to take those s orbitals and the p orbitals, we're going to mix them together, and they're all going to change into what we call hybrid orbitals. Hybridization is the combination of 2 or more atomic orbitals to form the same number of hybrid orbitals. So if you blend together 2 atomic orbitals, you'll get 2 hybrid. If you blend together 3 atomic orbitals, you'll get 3 hybrid, and so on and so forth. So here, instead of having a 2s that's singly occupied and a 2p, 3 of the 2p's that are singly occupied, we will go ahead and promote that electron up, but then the 2p orbitals are going to come down in energy sum, and the 2s orbital is going to go up in energy sum, and we will have 4 equal energy orbitals. And those 4 equal energy orbitals we'll call sp3 hybridized orbitals. By the way, the word for same energy orbital is degenerate. I don't test you on that, but you may have remembered that from general chemistry. All right, so we've got 4 orbitals. Now, the shape of those orbitals, what that looks like. So the shape and the orientation of those orbitals. So we know that s orbitals are spherical and that p orbitals are dumbbell shaped. Well, when we take one s orbital and 3 p orbitals and mix them together, we're going to get 4 orbitals that are sp3 hybridized orbitals. And they're going to have some of the p character and some of the s character. The p character is the dumbbell shape, and the s character is the spherical shape. So it'll end up being a lopsided dumbbell. All right. The four orbitals will rearrange themselves according to the valence shell electron pair repulsion theory. In other words, they'll try to get as far away from each other as possible. And when they do, so these are the unhybridized orbitals, and the hybridized orbitals are going to arrange themselves in a tetrahedral arrangement. And that tetrahedral arrangement is when we have the four domains. And so what we learned earlier, when we have four domains, is tetrahedral. Well, we also now know that when we have four domains, it is also sp3 hybridized. All right. So let's look at bonding using the sp3 hybridized orbitals. For methane, we have the overlap of the sp3 hybridized orbital on carbon with the 1s orbital on hydrogen. All right, these four bonds point to the corners of a tetrahedron, and we call that tetrahedral. So we call it tetrahedral. All right, so here's our ball and stick. This is like the picture that I showed you guys a few minutes ago. There's the picture. Okay. And then there is a sp3 hybridized orbital. There's actually four of the sp3 hybridized orbitals on carbon, and each hydrogen has a 1s orbital, and the overlap of those singly occupied orbitals will make some sigma bonds between carbon and hydrogen. Just as a reminder, all single bonds are sigma bonds. All single bonds are sigma bonds. So anytime you have a single bond, it is a sigma bond. All right, so now what we want to do is we want to look at the trigonal planar electron domain geometry and the linear electron domain geometry and match up with their hybridizations. For trigonal planar, again, we'll go back to the orbitals. Instead of hybridizing all four of the orbitals that are available, we're going to only hybridize three of them. We're going to leave one of them unhybridized. So we're going to mix together this 2s and these two 2p orbitals, and we'll get sp2. Hopefully by now you'll see that the superscript tells you how many of the p orbitals you mixed in. The superscript for s is 1, but it's implied, so we don't put the 1. So it's just, we have sp3, sp2. Here in a minute, I'm going to show you sp. You will notice that there is an unhybridized p orbital on there, and so we can have that unhybridized p orbital. Sometimes it will have electrons in it, and sometimes it won't. In the case of boron trifluoride, we'll find that there is the overlap of the sp2 hybridized orbital on boron and the singly occupied 2p orbital on fluorine, and we can get a sigma bond there. We get three of them. Perpendicular to that trigonal planar arrangement, so perpendicular to that, we have an empty p orbital, and that's that 2p orbital there. It is empty. That empty p orbital has a lot of reactivity, particularly in this molecule. It makes it very capable of accepting lone pair, or not lone pair, any pair of electrons from other things. So that BF3 ends up acting as what we call a Lewis acid. We'll talk about that in the next chapter. All right. Just as a reminder, here is a BF3. Here's the BF3 molecule that I 3D printed. There's the boron in the middle. There's the fluorines on the edge. And we have that trigonal planar symmetry with a 180-degree angle. All right, for sp hybridized things, and the example that we have here is BeH2. So you'll notice that we took one of the 2s and one of the 2p. We mixed them together to make sp hybridized. You'll notice the subscript here on p is now 1, so we don't have to write it. And so there we go. We have the sp, and we have two unhybridized 2p orbitals that are on that whatever that atom is. In this case, it would be beryllium. Now I'm going to switch back over real quick. Here I've got beryllium chloride, which is going to be very similar to the beryllium hydride that I have on that other page. And you'll see that the electron domain geometry is linear. The angle between those is going to come out to 180 degrees. All right. When it comes to determining what the hybridization is, well, this turns out to be really easy. You just count the number of domains, and if you can tell how many domains there are, then you can tell the hybridization. So just count the number of groups or domains, and that will tell you what the hybridization is. So if you know something has 4 domains and it's tetrahedral, then it must be sp3. If you can tell something has 3 domains and it's trigonal planar, then it must be sp2 hybridized. And finally, if you've got 2 groups and so only 2 domains, then you're going to have sp hybridized. All right. Let's look at a couple of hybridization examples. The first example we want to look at is with ammonia and water. And with ammonia and water, we've got 4 groups around each. With 4 groups, that means that these are both sp3 hybridized. All right. So there's an sp3 hybridized orbital, singly occupied sp3 hybridized orbital that overlaps with the 1s orbital on hydrogen, and we've got 3 of those on the ammonia. And then we have a lone pair of electrons in an sp3 hybridized orbital that's also on the nitrogen. So again, 4 sp3 hybridized orbitals, but one of them has a lone pair of electrons. With water, similar thing. We've got an sp3 hybridized orbital overlapping with hydrogen, the 1s orbital on hydrogen. Same thing here. But then we've got two sp3 hybridized orbitals with lone pairs on the oxygen. For ethane, so this is C2H6, we'll find that both of the carbons are sp3 hybridized. So that means that we again have the sp3 hybridized orbital overlapping with the 1s orbital on hydrogen, 6 of those. And then we've got the carbon sp3 hybridized orbital overlapping with another sp3 hybridized orbital to make a sigma bond between the 2 carbons. All right, there's something interesting about ethane, and before we do that, before I show you something interesting, let me bring my model of ethane here. So here is a molecular model. Again, I 3D printed this at my workshop here in my house, and so here we've got the sp3 hybridized orbital on carbon overlapping with the sp3 hybridized orbital on the other carbon. And so that is ethane. Now, something that is interesting about ethane is that when you make the model, you will see that you can rotate about the carbon-carbon bond. So you get free rotation about that carbon-carbon sigma bond. And so that means that the atoms that are on this are not locked in the orientation to the atoms that are on this carbon. And so here I've got on my models, all right, I've got one where I have just painted hydrogen atoms, and you can see that you can rotate about the carbon-carbon sigma bond. And so so you can see that they are not locked into position. There's free rotation about that bond. And that's an important characteristic of ethane. All right. We now want to look at hybrid orbitals on ethylene. Ethylene, or sometimes called ethene, but ethylene is the structure we want to look at. So when we draw the structure, the Lewis structure for ethylene, we'll see that there are 3 groups around each carbon. There's a double bond, a single bond, and another single bond. So that's 3 groups. That means it's trigonal planar, and that also means that it is sp2 hybridized. Angle is going to come out to approximately 120 degrees. I don't know if it's exact, but it comes out pretty close. So that means that the one of the bonds that's between the two carbons here, one of the bonds is between the sp2 hybridized carbon on sp2 orbital on carbon and the other sp2 hybridized orbital on carbon, and that they overlap to make a sigma bond directly between those two carbons. There's also an unhybridized p orbital. So when we make it sp2 hybridized, we have an unhybridized p orbital, and that unhybridized p orbital has an electron in it, so it can overlap with other orbitals, and I'll show you that that's what happens. So here the sp2 hybridized orbitals are left out of this picture, but here we've got the two p orbitals. Those two p orbitals are perpendicular to the plane of the molecule, and so there's a p orbital there and a p orbital there, and those two p orbitals overlap above and below to give a pi bond. That is the second bond in this structure. Now, I've got a model that I've made of ethylene here. So here is my model of ethylene, and you'll see that we've got the sp or the sp2 hybridized orbitals that are overlapping to make this blue sigma bond that's in between the two carbons. We've got the sp2 hybridized orbital overlapping with a 1s orbital on hydrogen to make a sigma bond here, here, there, and there. And then there are p orbitals that are perpendicular to the molecule, and those p orbitals overlap above and below that internuclear axis, and that makes one bond. So there's a single bond, there's one bond there, and there's another bond that's represented by both of these lobes. All right. Now I'm going to go back over here to this picture, and you'll see that I've got where it says there's a link on the carbon, and that link on the carbon is a special graphic, and I'm going to load that graphic up. All right, so here is that graphic. And so here we've got the carbon is at this position and this position. The purple orbitals here are sp2 hybridized orbitals. You've got two that are overlapping with the 1s orbitals on these hydrogens. Same thing happening over here. And then here is an sp2 hybridized orbital that is going to overlap with the sp2 hybridized orbital on this carbon. And so as we bring them closer together, we start to get overlap, and when we get close enough, they will make a sigma bond. And so that is the sigma bond between these two carbons. If we bring them a little bit closer, we can start to get overlap above and below to make that pi bond. And so that pi bond would represent, that pi bond would be the second bond in that. Whenever we have multiple bonds, the first bond is always a sigma bond. Any subsequent bonds are going to be pi bonds. So if you have a triple bond, you end up having two pi bonds. And I'll show you what that looks like here in just a moment. Anyway, this particular graphic comes from Pearson. It's a different textbook provider, but it is a pretty cool graphic, so I like to use it. All right, so that is for ethylene. Now we want to look at when we have ethylene, we do not get free rotation about the carbon-carbon bond. And that's because of the pi bond. The pi bond does not allow rotation around that carbon-carbon bond. And so that means that if you have different substituents, something other than hydrogen on the carbon, that they are locked in place relative to each other. So for example, here we've got two groups that are on the same side of the pi bond, but if you were to flip it around, they would be on opposite sides. Well, it turns out that if you have this molecule, you cannot easily interconvert to this molecule without heating up your sample pretty substantially. And so you'd have to heat it up quite a bit, and you can convert it. Conversely, if you heat this one up, you could get some of this back, but these are not the same molecule. These are what we would refer to as stereoisomers. They are isomers that are not constitutional isomers. They have the same connectivity. So you can see that here we've got one white atom and one blue atom connected to a carbon, a double bond, one white atom and one red atom connected to a carbon. Well, it's the same thing over here. They just oriented in space differently. So we refer to these as stereoisomers. I've got an example of this. And so again, get my camera out. So I've got an example of this where, so here you'll see these two red atoms are on the same side. The reason we can't rotate about this carbon bond is that this pi bond, in order to rotate, we would have to break that pi bond. So we would have to add enough energy to this molecule to break that pi bond. And then we could rotate around and get the other structure. And I just so happen to have the other one here. So these two are on the same side, and you'll see these two are on opposite sides. And these do not interconvert between each other. We'll find, and it depends on what these atoms are, but we'll find that the one where they're on the same side and the one where they're on opposite sides often will have different physical properties, chemical properties, or at least somewhat different chemical properties, and they'll have different energies. So they are different molecules. Again, they're not constitutional isomers, they are stereoisomers. When we get to chapter 5, we're going to have a whole chapter talking about stereoisomers. So those are those stereoisomers. Interesting stuff. All right. Now we want to look at ethylene, or not ethylene, acetylene. And acetylene here has a carbon-carbon triple bond. We'll see that there are two domains, meaning this is linear. And when there are two domains, that also means that it is sp hybridized. When it's sp hybridized, that means we took one s and one p orbital. We blended them together to make two sp orbitals. But that also means that we have two p orbitals that are unhybridized. So here we've got an sp hybridized orbital on carbon overlapping with another sp hybridized orbital on carbon to make the sigma bond between the two carbons. We have an sp hybridized orbital on carbon overlapping with a 1s orbital on hydrogen to make the sigma bond there, and the same thing happening here. Those two p orbitals are perpendicular to this linear molecule, and they look like this. So we've got, they are perpendicular, and we'll find that one pair will overlap above and below that internuclear axis to give a pi bond, and one will overlap in front and in back to give us the other pi bond. So not only are these p orbitals perpendicular to the molecule, they are perpendicular to each other. And this is what that molecule would look like. Again, I've got a model of this. So a sigma bond, the blue one here is also a sigma bond. It's the overlap of an sp orbital on a carbon and an sp orbital on this other carbon. And then we've got a pi bond that is above and below that internuclear axis, and we've got a pi bond that's in front and in back. All right. And so that is a molecular model of acetylene. And again, this is one that I 3D printed and made myself. So we want to look at number 70 on the in-class assignment. And I'm going to lower my camera down here a bit. All right. So number 70. All right, and we want to say what orbitals are used to form each of the indicated bonds. And if we've got a single bond, then we have to list just one of the bonds. If we've got a double bond, then we'll need to list two bonds. So here we've got a carbon and a hydrogen. Well, we know hydrogen just has a 1s orbital. And since it's a single bond, it has to be a sigma bond. So for that first one, it is a sigma bond. And it is the overlap of a carbon, and we need to see what the hybridization is of this carbon. When we count, there are 4 domains around that carbon. That means that that carbon is sp3 hybridized, and it overlaps with the 1s orbital on hydrogen. So that is that one. And then here we've got a carbon and another carbon. It's a single bond, so it has to be a sigma bond. And they are both sp3 hybridized. Remember, there are 2 implied hydrogens on each of those carbons. So we will have a carbon sp3, carbon sp3. And that takes care of that one. All right, now let's look at these 3. And so for the first one, I'm going to number these 1, 2, 3. For number 1, we've got a single bond, so it is a sigma bond. And we've got an sp2 hybridized orbital on carbon, because this is there's 3 domains, so that's sp2. So we'll put carbon sp2, and then the hydrogen. Well, all hydrogens have a 1s, so I'm going to put 1s there. For this second one, we've got 2 bonds. We've got a sigma. There's always going to be 1 sigma bond, and then any other bonds will be pi bonds. And so for 2, we'll have a sigma bond, and this carbon is sp2 hybridized, as is this one. So we will get a sigma carbon sp2 carbon sp2. As for the next bond, the pi bond, it is going to be a carbon 2s, or 2p orbital rather, carbon 2p. So those are the unhybridized p orbitals that are perpendicular to that sigma bond. And again, they overlap above and below. For our third one, we've got a single bond, so it's a sigma bond. Again, anytime you have a single bond, it's a sigma bond. And we've got 2 different hybridizations. This carbon is sp2 hybridized, while that one is sp3. So we'll put carbon sp2, carbon sp3. And that is the bond length there. All right, are the bond hybrid orbitals. So next, we've got 2 that we want to look at. So I'm going to just, again, number these 1 and 2. For the first one, it's a single bond, so it has to be a sigma bond. We've got the carbon here is sp3 hybridized, because there's 2 implied hydrogens there. And this carbon has 4 bonds, but there are 3 domains. There's a double, a single, single, so that one's sp2. So we'll put carbon sp2, carbon sp3. And that is going to be that sigma bond. Between the carbon and oxygen, we're going to have 2 bonds. All right, we have one that is a sigma bond, and the carbon we've already determined is sp2 hybridized. If we look at that oxygen, it's got 3 domains around it, so it's also sp2 hybridized. So we will have sigma carbon sp2 and oxygen sp2. And then there's a second bond, and the second bond is always a pi bond, and that'll be a carbon 2p. And oxygen, since oxygen's in period 2, it's also a 2p orbital. All right, next, let's look at this one. So here we've got carbon, hydrogen, and again, I'm going to number these. So 1, 2, 3, and 4. And for 1, I'm just going to kind of put it over here on the edge. So 1, that's a sigma. And the carbon, if we look at that carbon, it's got 2 domains around it. So that carbon is sp hybridized. So carbon sp. And then the hydrogen is 1s, as all the hydrogens are. So that's our sigma bond there. For this, the number 2, we've got 3 bonds, so we'll have a sigma and 2 pi bonds. Now, the two pi bonds are going to be identical, but I'm going to go ahead and write them both down. The sigma bond, this one is sp hybridized. That one's also sp hybridized. So we'll have carbon, sp, carbon, sp. And that's our sigma bond in that triple bond. For the pi bonds, we'll have a carbon 2p overlapping with another carbon 2p. Same thing for the other pi bond, carbon 2p, carbon 2p. All right, so we've accounted for 4 bonds. Let's look at the third one here. Our third one, it's a single bond, but we need to look at, so single means sigma, and we need to look at the hybridization. We already determined that this carbon was sp hybridized. This carbon has 3 domains around it, so it is sp2. So we'll have carbon, sp, carbon, sp2. And then finally here we've got nitrogen. That nitrogen has a lone pair on it. It's not expressly drawn, but because it's neutral, we can tell that there's a lone pair on it. That means there are 3 domains around that nitrogen. And with 3 domains, that means it is sp2 hybridized. So for our fourth bond, we will have a sigma bond, and the nitrogen will be sp2 hybridized. And our carbon, it's got 3 hydrogens on there and then a bond going to the nitrogen. So that means that that is sp3 hybridized. So carbon sp3. All right, and that is how we identify our hybrid orbitals. Okay, so we're getting a little long on the video, but I'm going to go ahead and just keep on going so that we can get this one in the books here. We now want to look at bond length and bond strength. And so when it comes to bond length, we will find that that as we increase the number of bonds between 2 atoms, we will increase the strength of the overall bond. So a double bond will be stronger than a single bond, and a triple bond will be stronger than a double bond. All right, but we'll also find that those bonds, as they become stronger, will become shorter. So a triple bond will be shorter and stronger than a double bond, and a double bond will be shorter but stronger than a single bond. And so this is the trend. So we will find, again, the more bonds, the stronger it is, and also the shorter that bond is. We'll find that there is an effect from hybridization on the length and strength of the bonds. And so that effect is the length and the strength of the bond depend on the hybridization. And we'll find that, that an sp3 hybridized orbital overlapping with a 1s orbital on hydrogen is going to give us a longer and weaker bond than an sp2, which is longer and weaker than an sp. All right, so we will find that this will be the longest and the weakest, and the sp will be the shortest and the strongest. Now, to give you some numbers that go with this, that's what I have on the next page, are some numbers. For the carbon single, double, and triple bonds, these are the bond lengths. So a carbon single bond is, let's see, 153 picometers. The double bond, 134. The triple bond, 121. So you'll see there's a pretty significant difference in the bond lengths depending on the number of bonds between those 2 atoms. You'll also see that there's a pretty significant difference in the bond energies. The single bond is worth, in this particular molecule, it's worth 368 kilojoules per mole. The number in parentheses is kilocalories. You kind of have to bear with me as I go through these. I learned these all in kilocalories per mole and memorized them way back when. And really, most textbooks use kilojoules per mole now, which it's just the favored way to do it. So I try to use the kilojoules per mole. So anyway, the double bond, you'll see it's not quite twice as much as a single bond, but it is significantly higher. And the triple bond is not 3 times as much, but it is significantly higher than the single or the double. Now, for the carbon-hydrogen bonds, you will see that a carbon-hydrogen bond that's sp3 hybridized, bond length of 111 picometers. For the sp2, it's a little bit shorter, about 1% shorter at 110 picometers, and for sp, about 109. Those are pretty subtle differences in bond lengths, but there is a reason that they are that these are shorter, and I'll show you that reason here in just a moment. For the bond strength, even though these are pretty small differences in bond length, these are pretty significant differences in bond strength. The sp3 hybridized carbon-hydrogen bond is worth 410 kilojoules per mole. For sp2, it's 435, so that's a pretty significant increase. And then look at the huge jump between sp2 and sp hybridized. So that's a big increase in the bond strength. All right, and so now we want to look at the percent S character, and this is a good explanation for why it's a good explanation for why the bonds are shorter for sp than they are for sp2. We'll find that the more S character there is, the more rounded the orbital is, and the shorter that orbital is. So the more S character there is, the shorter the bond and the stronger the bond is going to be. So 50% S character for sp, that's going to be a stronger bond than sp2 at 33% S character, sp3 at 25% S character. So let's look at number 74 before we go to that next section. And it says rank the following in order of increasing bond length. All right, so here we've got a triple bond, there we've got a double bond, and there we've got a single bond. Okay, this is not a very hard problem because they are already in order of increasing bond length. This one is the shortest, and this one is the longest. And this one, of course, is in the middle. So the more bonds, the shorter it is. The fewer bonds, the longer it is. All right, on this one, we're trying to compare these three. So here we've got an sp, here we've got sp2. All right, again, this is in the same order. This one should be the shortest, and this one should be the longest. All right, I should probably rework that problem and make it a little bit more challenging. All right, so that is that. Let's go back. And we'll talk about electronegativity and polarity. Again, this is something that you've seen before in general chemistry. And I just like to wrap it up and show it to you again. So electronegativity is it's a measure of an atom's ability to attract electrons to itself in a bond. The more electronegative something is, the more it pulls electron density to that atom. The most electronegative element on the whole periodic table is fluorine. Oxygen is a moderate distant second, and then we'll find nitrogen and chlorine are sort of fourth and third there. And then it kind of tails off as we get further away from fluorine. Now, these numbers are approximations, and these approximations are used to help you estimate dipole of a bond. Really, this is not a perfect system, but it is a pretty good system for giving us an estimate. For very small differences, we'll find that bonds tend to be nonpolar. For very large differences, they tend to be ionic. For sort of the in-between distances, we'll find that the bonds tend to be polar. All right, so again, fluorine is the most electronegative. I recommend just kind of getting an approximate. You don't necessarily have to memorize these, but get these down pretty well. And it's not too bad. That's a limited number, so you can do it. All right, so when it comes to bond polarity, The bigger the difference, the more polar the bond is. We'll find that if you have a very small difference in electronegativity, so a difference of less than approximately 0.4 in your electronegativity, then that's usually going to indicate a nonpolar bond. So for example, here we've got carbon-carbon. Well, they're both an electronegativity of 2.5. That means that that bond is going to be completely nonpolar. The electrons will be shared evenly between those two carbons. Between carbon and hydrogen, carbon's 2.5, hydrogen's 2.2. That's a difference of about 0.3. And with it being a pretty short bond, we will find that this ends up being considered a nonpolar bond. Now, once that difference in electronegativity gets greater than about 0.4, we generally will consider it a polar bond. And an example of a polar bond would be carbon and oxygen. Carbon is 2.5, as we saw here. On the previous page, it said that oxygen had an electronegativity of 3.4. So 2.5 and 3.4, that's a difference of 0.9. That's a fairly polar bond. The bigger that difference, the more polar we would consider that bond. So the bigger that difference, the more polar we would consider that bond. If the difference gets bigger than about 1.8, we generally are going to get into ionic bond territory. However, there are some notable exceptions to that. So this is why, and I'm going to go back to this page. This is why if you have something like sodium chloride, well, sodium is 0.9 and chlorine is 3.2. That's a difference of 2.3. Well, that's an ionic bond. And so you get up in that 1.8 and higher, you generally are into ionic territory. When it comes to the polarity of individual molecules, we need to look at the whole picture. We can't just look at the individual bonds. We have to look at the individual bonds and also look at the shape. Most of the time, this isn't too terribly difficult. So we'll use electronegativities to identify the polar bonds and the directions of those bond polarities. The dipoles between those bonds are usually represented by vectors, it's just a number that has a direction. And then if we add those vectors together, we can determine if that molecule is going to be polar. All right. Sometimes when we add the dipoles on a molecule together, we'll get something that is nonpolar. They cancel each other out. Sometimes when we add dipoles together, they reinforce each other, and we will get something that is polar. So here is an example of a polar molecule. We've got a bond dipole between carbon and chlorine. Carbon has an electronegativity of 2.5. The chlorine was I think it was listed at 3.2 on there. So that's a difference of 0.7. It's pretty significant. So the carbon-chlorine bond is fairly polar. The carbon-hydrogen bonds, as we talked about earlier, are essentially nonpolar. They are very low polarity, and so they don't cancel out this bond dipole. That means that the whole molecule is polar. We can represent how polar a molecule is by looking at what's called an electrostatic potential plot. The more negative charge there is on something, generally we'll represent that in red. So we have a partial negative charge, the delta minus that's on the chlorine, and we have a delta plus that is on the carbon. So the bigger that difference in delta minus and delta plus, so the larger the charges are, the more polar that bond and therefore the molecule is going to be. If we look at a couple of polar molecules, and here we're going to look at water as an example of a polar molecule. It has more than one polar bond, but it also has that lone pair or two lone pairs of electrons. So it's got two bonds that are polar and two lone pairs. Because these two bonds are at an angle to each other, about 104.5 degrees. That means if we add these two vectors together, we get a net dipole. And you'll see that both of these are pointing up a little bit. That means we have a net dipole where there is a partial positive charge near the hydrogens and a partial negative charge on the oxygens. So water ends up being a polar molecule. I have an electrostatic potential map on the last page, and I'll show that to you here in just a moment. But before I do that, let's look at a nonpolar molecule, carbon dioxide. So carbon dioxide is a good example. It's linear. The two dipoles are exactly opposite. Let me pull that up. So here's carbon dioxide. We've got a pretty strong dipole between carbon and oxygen, another one between the carbon and the other oxygen. But since they're exactly opposite directions and exactly the same strength, they cancel each other out. So carbon dioxide is considered a nonpolar molecule. So it is nonpolar. So here are the electrostatic potential maps of water and carbon dioxide. And so you'll see the partial positive on the hydrogens, the partial negative on the oxygen, and that gives us a overall polar molecule. With carbon dioxide, we do have a partial negatives on the oxygens and a partial positive on the carbon. However, because they're exactly opposite, they cancel out and we have zero net dipole. All right, and then we're going to do number 84, and after that, look, that's my favorite in every chapter, favorite page in every chapter. So we are at the last problem. So let's go to number 84 on the in-class assignment. And we've got this antibiotic called amoxicillin. And here we're going to answer questions about each of these. So it says, predict the hybridization and geometry around each indicated atom. So the ones with arrows. Well, that carbon has 3 domains. So the hybridization is sp2, and the geometry is trigonal planar. All right, so that is that carbon. So we'll want to look at this nitrogen. This nitrogen has a bond to carbon, 2 bonds to hydrogen, and there is an implied lone pair. So there is an implied lone pair that is there. So that's 4 domains. That means it is sp3 and will be tetrahedral. Now, tetrahedral is the electron arrangement. The molecular geometry, because one of those is a lone pair, we could call it trigonal pyramidal. So trigonal pyramidal. All right, we've got another carbon here. This carbon has, this carbon has 4 things around it. So it is sp3 hybridized, and it is also tetrahedral. All right, and then this oxygen, we'll go ahead and do this one. It has 2 lone pairs on it. And so since it's got 2 lone pairs, we'll have 1, 2, 3 domains. That's sp2. And it is trigonal planar. All right, so that's the hybridization and geometry. Label 5 polar bonds using the symbols delta plus and delta minus. Well, it turns out there's a lot of polar bonds here, but I'm just going to label a few of them. So here between oxygen and carbon, so we'll have a delta minus on the oxygen and a delta plus on the carbon. We would also have the same thing happen between oxygen and hydrogen, but we'll just label some of the interesting ones here. All right, so here we've got a carbon nitrogen, carbon electronegativity of 2.5, or was it 2.4? Anyway, 2.5, and nitrogen was 3.0. That's a difference of 0.5. So we'll put a delta plus on that carbon and a delta minus on that nitrogen. On this carbon, we'll have a delta plus on the carbon and a delta minus on the oxygen. For this NH, we'll have a delta minus on the nitrogen and a delta plus on that hydrogen. We'll go ahead and do a couple more of these. Delta plus on that carbon, delta minus on that oxygen. All right. We also have a delta minus on that nitrogen. And then here we'll look at this one, delta plus on the carbon, delta minus on the oxygen. We also have what? A delta plus and delta minus here. So delta minus, there's another polar bond. There's a lot of polar bonds in this. So a lot of polar bonds. I may have missed one, but we got most of them. We didn't get the OH and the OH here. All right, draw a skeletal structure. So draw a skeletal structure. All right, I may need more space here, but well, we'll figure it out. All right, so for this, we'll draw. All right, so we'll draw a hexagon to represent that benzene ring, and then we'll put those pi bonds in there. We don't need to put the hydrogens in, but we will put the OH there. And then we've got a carbon, another carbon, a nitrogen, and then here we'll put NH2. So here is our we have a carbonyl right there. That's that carbon oxygen. And then we'll put NH for that. All right, we'll put carbonyl there. We do have a nitrogen there. Sulfur. Nitrogen. Okay, and we'll put 2 methyls there. And then here, there's an implied hydrogen, and we'll do, I'm just going to put COOH there to indicate the carboxylic acid functional group. All right, so that's our skeletal structure. How many pi bonds does it have? All right, well, we just need to look at the number of double bonds. So 1, 2, 3, 4, 5, 6. So we'll have 6 pi bonds. So 1, 2, 3, 4, 5, 6. 6 pi bonds. Find a carbon hydrogen containing a carbon atom having a hybrid orbital with 33% S character. Well, 33%, so 33%, that equals sp2. So we just need to find a carbon hydrogen where where it is sp2. And there's several examples, but I'm just going to pick one of these that's on the benzene ring, and that's going to represent most of them right there. So that carbon is sp2 hybridized, so it has 33% S character, and there is the bond. In case you're curious, there are 3 more there. Or 3 more, so 4 total. And I'm not seeing any others that are sp2 hybridized. Now, well, I see this, we've got a couple of carbons here that are sp2 hybridized, but they don't have hydrogens on them. So, all right, so that represents the end of chapter 1. And again, there is that. So you look for chapter 2.